Alright, non-resident training course, September 1998, Navy Electricity and Electronics Training Series Module 7, Introduction to Solid-State Devices and Power Systems, Navy Trial 14179, Distribution Statement A, approved for public release, distribution unlimited. Alright, Chapter 1, Semiconductor Diodes, Chapter 2, Transistors, Chapter 3, Special Devices, Chapter 4, Solid-State Power Supply. Appendix, Glossary, and Perpendicular Periodic Table Elements Index. Alright, Chapter 1, Semiconductor Diodes. Learning objective. The learning objective is with the beginning of each of the chapter of the learning objective with the preview of the information you're expected to learn in the chapter. The comprehensive check questions are based on the objective basic successfully complete the NRTC, and you indicated you may have met the objective learning of the information learning objectives listed below. Upon completion of this chapter, you should be able to do the following: state in terms of the energy band the difference between conductor, insulator, and semiconductor. Explain the electron hole flow theory of the semiconductors, how the semiconductor is affected by doping. Define the term diode in the brief description, construction, and operation. Explain how diode can be used the halfway rectifier and a switch. Identify diode symbology, alphanumeric designation, color code. List the precautions that must be taken when working with the diodes. Describe the different ways to test them. Introduction to solid-state devices. As you recall, the previous design of the industry with the semiconductor electronic properties somewhere between those of the insulator and conductor. The semiconductor materials electronic component is not new. Some of the devices are as old as the electron tube. Two of the most widely known semiconductors in use today are the junction diode and the transistor. Semiconductors follow the more general heading of the solid-state device. The solid-state device is nothing more than an electric device which operates on virtue much of the movement of the electrons with a solid piece of semiconductor material. Since the invention of the transistor, solid-state devices have been developed and improved at an unbelievable rate, with the great strides that have been made with the manufacturing techniques. There is no foreseeable limit to the future of these devices. Solid-state devices are more made of the semiconductor materials, often complete in compactness, efficiency, ruggedness, versatility. Consequently, these devices have invaded virtually every field of the science and industry. In addition, with the junction diode transistor, a whole new family of related devices have been developed: the zero diode, light emitting diode, and field effective transistor. When one of development has dominated solid state technology, probably has greater impact on electronics industry than either electronic tube or transistor is in the integrated circuit. The integrated circuit is a minute piece of semiconductor material that can produce complete electronic circuit functions. As the application for the solid-state devices and the need for the knowledge of these devices becomes increasingly important, personnel of the Navy today will understand solid-state devices if they become the proficiency for the repair of the maintenance of the electronic equipment of the Air Force. Our objective of the module is to provide the broad coverage of the solid-state devices, broad application, power supply, and we'll begin with a discussion, some background information for the development of the semiconductor with we'll propose. We'll proceed with the semiconductor diode, transistor, special device family, and solid-state power supplies. Although semiconductor was late semiconductor development. Although semiconductor was reaching the present development of the story began long before the electron tube. Historically, we can go back as far as 1883. Michael Furr had discovered the silver sulfide semiconductor, the negative temperature coefficient. The negative temperature coefficient is just another way of seeing its resistance, electronic current flow that decreases as the temperature increases. The opposite is true for the conductor and positive temperature if coefficiency. The of the particular characteristics semiconductors use extensively in the power measuring equipment. Only 2 years later, another valuable characteristic reported by Monk and A. Rosenhold, he found that the certain materials with rectifying properties, strange as it may seem, is given as such little notes that had little rediscovered in 39 years later by F. Braun. Today, close to the close of the 19th century, experimental to begin with the notice of the particular characteristics of the chemical element selenium. Discovered that additional rectifying property for the ability to convert AC into DC. Selenium was also light sensitive and resistant to the decrease by the increase of light intensity. The discovered eventually led to the invention of the photophone by Alexander Graham Bell. The photophone was converted various lights into sound with the predecessor of the radio receiver. However, it was until the actual birth of the radio celluloid was used to an extent. Today, celluloid is an important widely used as semiconductors. Many other materials was tried and tested for use in communication. Silicon was found to be the most suitable materials tested by, while galena, a crystalline form of lead sulfide, was found most of the sensitive for use for the early radio receiver. The 1915 Carl Burdix discovered germanium, another metallic element that also had rectifier capabilities. Later became widely used with electronics, low power, low frequency applications. Although semiconductors were known long before the electron tube was invented, the semiconductor device at the time could not match the performance of the tube. Radio needed a device that could not only handle power but amplify the rectifier to detect all signal as well. Since tubes could do all these things, semiconductor devices of the day could not. The semiconductors soon lost out. It wasn't until the beginning of the World War II that the interest renewed and the semiconductor, therefore the dire need for the device that could work with the ultra-high frequencies of the radar. Electron tubes enter electrode capacitances that were too high to do the job. The point of contact semiconductor diode, on the other hand, very low internal capacitancy. Consequently, it filled the bill and could design to work with the ultra-high frequencies used in radar, while electronic tube could not. As radar took on greater importance, communication electronic equipment became more sophisticated. Depends on the better solid state of the device's mount. The limitation of the electron tube made necessary. Of course, if something new, different, and amplifying device was needed, it was with a smaller, lighter, more efficiency capable of handling extremely high frequency. This was asking a lot, but if the progress was to be made, the requirements had to be met. The serious study of the semiconductor materials began in the early 1940s and has continued since. In June 1948, a significant breakthrough took place in the semiconductor development. That was to discover the point of contact transistor. Here was the semiconductor could amplify the discovery that brought the semiconductor back into competition with the electronic tube. As yet a year later, with the junction diodes and transistors developed, the junction transistor was found superior to the point of contact type of many respects. The comparison with the junction transistor was more reliable, generated less noise, had higher power handling ability in the point of contact Then junction transistor became a rival electron tube and many used the previously uncontested. Semiconductor diodes were not were not to be slighted. The initial work of the doctor called Zenier led that the development of the Zenier diode, the frequently used today, regulate the power supply's voltage to precise levels. Considerably more interesting than the solid-state diode was generated by Dr. Leo Esky, Japanese scientist, fabricated the diode that could amplify the device named the tunnel diode. Has amazing fast switch capabilities, although it was used with the conventional amplifying oscillation circuit. Its primary use with the computer logic circuits. Another breakthrough came in the 1950s when it was discovered that semiconductor materials could be combined and treated with the function of their entire circuit. Some assemblies rather than as in-circuit components. Many of the names have given the solid circuit concept with the integrated circuit with the microelectronics microcircuitry. So as we see, looking back with the semiconductors, not something new, but it has come a long way in a short time. Semiconductors application. In previous paragraphs, we've mentioned just a few minutes of many different applications of the semiconductor device. Even the device has become widespread, as it would be impossible to list all the different applications. Instead of the broad coverage of the specific application is presented, semiconductors are all around us. They can be found in just about every commercial product with a we touch them from the family car to the pocket calculator. Semiconductor devices are contained in the television set, portable radio, stereo equipment, and much more. Special science industry also rely heavily on semiconductor devices. Research in the laboratories upon the devices also such as electronic instruments to perform tests and measurement, numerous other experimental tasks, industrial control systems such as those manufacture automobiles, automatic telephone exchange with the semiconductor for today, the heavy-duty version of the solid-state rectifier diodes also have been very used to convert large amounts of the power of electrical arrows of many of the different applications of solid-state devices. Space system, computers, data processing equipment are some of the largest consumers. The various type of the modern equipment is literally loaded with the semiconductor devices. Many radar communication airborne equipment are transistorized data display systems and data processing computers, aircraft guidance and control assemblies. Also good examples of electronic equipment that use semiconductor devices. All these specific applications semiconductor devices would make long, impressively list. This is the fact that the semiconductors are being used extensively in commercial products industry and the military. or your semiconductor component competition. It should not be difficult to conclude that for what you already know, the semiconductor devices can and perform a conventional functions of the rectifying, application, oscillation, timing, switching, and sensing. Simply, you say these devices perform the same basic function as electron tube, but they perform more efficiently, economically, and for a better time period of time. That it should not surprise you to see that these devices are using placing electron tubes. Keep in mind that you see with the natural logic to compare with semiconductor devices, electron tubes. Physically, semiconductor devices are much smaller than tubes. You can see Figure 1.1 for the difference of the quite evident. The illustration shows the commonly used tube sizes alongside of the semiconductor devices. Capability, the reduction size should be about as greater to 100 to 1 by the weight of the 1000 to 1 by the volume. Easier with the size reduction favored the semiconductor devices. Therefore, whenever miniaturization required or convenient, transistors are favored over the tubes. Bear in mind, however, the extent of the practical size reduction bigger factors. Many things must be considered. Miniature electron tubes, for example, may be preferred in certain applications due to transistor, thus keeping the size reduction a competitive area. Figure 1.1 shows the size of the comparison of electron tubes and semiconductors. Power is in a two-sided story. For the loss of power, the efficiency of the significant factor. Semiconductors have decided advantage of the true, mainly with the semiconductor device, and perform very well with extremely amount of the power. In addition, they require no filaments or heaters, as in the case of electron tube. For example, the computer operating with 4,000 solid-state devices may require no more than 20 watts of power. However, the same number of the tubes would require several kilowatts of power. For high power application, different story. Tubes have the upper hand. The higher power has no equivalent in semiconductor devices. This because the tube cannot be designed to operate with over 1,000 volts applied with the display and to its plate, whereas the maximum allowable voltage of the transistor limited to 200 volts, usually 50 volts or less. The tube can handle 1,000 watts of power. The maximum power output of the transistor generally ranges from 30 milliwatts to slightly over 100 watts. When it comes in ruggedness, life expensing the tube is still in competition. Design and the functional requirements usually indicated by the choice of the device. However, semiconductor devices are regularly long-lived, where they can construct with withstand extreme vibration, mechanical shock. They have been known to withstand impacts that would completely shatter the ordinary electron tube. Although the specially designed tubes render extensive service life expectancy transistor better than 3 to 4 times the ordinary electronic tubes, there's no known failure mechanisms such as open filament tubes on the limit of the semiconductor's life. However, the semiconductor devices do have some of the limitations, usually affected more by temperature, humidity, radiation than the tubes are. Alright, your semiconductor theory. To understand solid-state devices' functions as they do, you will have to examine closely the composition of the nature of the semiconductors and entail a theory of the fundamental of the study of the solid-state devices. Rather than the beginning of the theory, let's first become reacquainted with some of the basic information you studied concerning matter and energy. Neets 1 module. Atomic structure. In the universe we know it is today the divided into two parts, matter and energy. Matter, which of the matters which are main concern with the time is anything that occupies space and weight, rock, water, air, automobiles, clothing, even our body is a good example of matter. From this we conclude in the matter that may be found in one of 3 states: solid, liquid, and gas. All matter composed of either element, combination elements. As you know, the element substance cannot be reduced. Similar form of chemical means. Example of the elements in which of the contact every day with iron, gold, silver, copper, oxygen. At the present, there is only 100 known elements in which all matter is composed. As we work our way down the size scale, we come to the atom, the smallest particle in which an element can be broken down, still retaining the original properties of the atom of one element. However, they differ from the atoms of other elements. Since there is only 100 known elements, there must be over the 100 different atoms of the different atom of each atom of the element. Now let's consider that more than one element at a time. That brings us to a compound. A compound is a chemical combination of 2 or more elements: water, table salt, ethyl, alcohol, ammonia. All example of the compound. The smallest part of the compound, which has all characters of the compound molecule. Molecule contains some of the atoms of each of the elements forming the compound. Consider sugar, for example. The sugar, generally in terms of the sense it occupies space and weight, a compound basically consists of 2 more elements: 2 lumps of sugar crossed into the small particles. Each particle still retains original identifiable the property of the sugar. The only thing that is changed with the physical side of the sugar that continue the subdividing the process, grinding the sugar into fine powder. The result is the same. The dissolving the sugar in the water does not change the identifying properties, and despite the fact that particles of sugar are now too small to see even with a microscope, eventually we end up with a quality sugar that can be further divided into seizing into the sugar. The quantity known of the molecule of the sugar. The molecule is further dividing. Consists of three simple kinds of matter: carbon, hydrogen, and oxygen. The simple forms of the called elements. These simple elements consist of atoms of the molecule of the sugar is made up of atoms carbon, hydrogen, and oxygen. As we investigate the atom, we find that it is basically composed of electrons, protons, neutrons. Furthermore, the electron, protons, neutrons in one element identical to those for the other elements. Different kinds of elements, the number, the arrangement of the electrons, protons, and different each of the element. The electron carries a small negative charge of electricity. The proton carries a positive charge of electricity equal to opposed to the charge of the electron. Since the scientific that has measured the mass for the side of the electron and proton, they now know that how much of the charge each possesses. Both electron and proton have the same quantity of charge. Although the mass of the proton is approximately 1,827 times that of the electron, some atoms exist neutron called neutron. Neutron has the mass approximately equal to the proton over the no electrical charge. According to the theory of electron and proton, neutrons, the atom thought to be arranged in the manner of the similar miniature solar system. The helium and the atom, figure 1-2, the two protons, two neutrons have the heavy nucleus with a positive charge around two very light electrons revolve each of the part that takes around the nucleus and is called the orbit. The electron continues beginning with the active line of the orbit. The force of attraction from the nucleus to maintain the orbit around the nucleus. The electron have to travel the speed produced the common force equal to the attraction force from the nucleus. Just energy is required to move the space vehicle away from the Earth. The energy is required to move the electron away from the nucleus. Like space vehicle, the electron is said to have a higher energy level to travel the larger orbit. And since scientific experiments have shown the electron requires a certain amount of the energy to start the orbit, one is called the electron's energy level. The virtue of the just as in the motion alone. The electron contains kinetic energy. The most of the position that contains potential energy. The total energy contained in the electron kinetic energy plus the potential energy. The main factor determine the radius of the electron orbit. The electron remain in the orbit and does neither gain nor lose energy. Figure 1-2 show the composition of a simple helium atom. The protons, electrons, neutrons, and nucleus neutrons. Or the orbiting electrons do not follow the random path. Instead, they combine with a different energy level, the visual level of the shell, with the successful shell leaving speed with a greater distance from the nucleus shell. The number of the electrons required to fill them, particularly each of the polys. The conclusion principle simply state with the principle specifically each of the shell will contain a maximum of 2 times the neutron squared electrons, which correspond to the shell number that contain the one closest of the nucleus. By this principle, the second shell, for example, would be the 2 times 2 to the 8th, the 8 electrons will be filled. In addition, whether being the number of the shell with a given letter designation, starting with the shell with the closest to the nucleus, progress outward towards the shown in figure 1-3, the shell is considered to be full or complete whenever they contain following quantities: electron 2 came with the first shell, with 8 in the second, and 18 in the third shell, and so the accordance with the exclusion principle. Each of these shells, major shells, can be divided into subshells, which are the 4 labeled as SPDF. Major shell subshells are limited to the number of electrons contained. Thus, the subshell is complete with that contains the 2 electrons. P, the subshell with the 6. These subshells are 10, and F subshells are 14 electrons. Inasmuch as the K shell that contains no more than 2 electrons, it must have only one subshell. The subshell of the M is composed of the 3 subshells of the SPD. The electrons of the SPD subshells are added together. Total is found like 18. The extra number that would be filled with the M shell. With the notice the electron configuration copper is illustrated 1-4. The copper atom contains 29 electrons completely filled with the first 3 shells, with the subshells leaving 1 electron with the subshell with the N shell, with a list of all of the known elements of the number of electrons each atom contains the periodic table of elements. The periodic table of elements included in Appendix E. Shows copper, the sub-level K, L, and P, and then M, and S. Alright, valency atom's ability to combine with the other atom of the number of the electrons of the outermost shell of the atom of the determine the valency of the further region of the outer shell with the called the valency of the shell of the electron contained with the shell with the called the valency electron. The valency of the atom determines the ability to gain lose electron with the determine the chemical and electrical property of the atom. The atom is lacking one of the 2 electrons forms the outer shell will easily gain electrons complete the shell. Large amount of the energy is required to free any of the electron atom having the relatively small number of the electrons outer shell with comparison with the number of the electrons required to fill with the shell. Each easily leave the valence electron. The valency shell always refers to the outermost shell, the energy bands. Now you have become reacquainted with the matter and energy. We'll continue with the discussion with electronic behavior. Stated that the otherwise, the orbital electrons contained with the energy are confined with a defined energy level of the various shells of the atom represent these levels. Therefore, the moved electron with the lower shelf is a little higher with a certain amount of the energy is required. The energy from the form of the electrical fields, heat, light, and the energy, even bombardment of the other particles, figure to provide even enough energy with an electron, even if the energy supply with the short required all amount, that will cause the remaining present energy levels applying more energy with the need that will only cause the electron to move to the next higher of the shell, and the remaining energy will be wasted. Similar terms of energy is required with the units to move electrons from one shell to the next higher shell. The units are called the quanta. For example, the 1, 2, or 3 quanta. The electrons are also can use the loose energy as well. With the receiver, the electron loses energy. They must move it moves to a lower shell. The loss of energy sometimes, in small cases, appears as heat. Insufficient amount of the energy is absorbed by the electrons. Possible the electron to be completely removed with the influence of the atom. Covalentization. The atom loses the electron, gain with the electron process with the electron shell. Exchange the step of the ionization takes place with the transfer of the energy. The result of the transfer, the internal energy of the energy of the atom having more than normal amount of electrons acquired with a negative charge with the call with a negative ion. The amount with the give of some of the number of electrons left, the fewer negative charge of the positive charge with the call of the positive ion will come. We can define ionization process which atom loses or gains electrons. Up to this point, one discussion we have chosen the only isolated atoms. The atom space is hard enough of the gas with very little influence upon each other. They're very much like lone atoms, but atoms solid have the marked effect upon each other. The force of the bind with the atoms together greatly modify the behavior of the other electrons. Consequently, the close proximity of the atom's individual energy level atom to break up the band's energy. The discrete is separately complete with the energy level that still exists for the energy band, but they are more than an energy level that were isolated with the atom, and in some cases the energy levels will have disappeared with the figure 1.5 difference for the energy arrangement between isolated atom in the solid state. Note the isolated atom, such as the gas, has the energy level, whereas the atom solid has the energy level of the group that has energy bands. Figure your energy arrangement and atoms energy level to number 1, 2, 3, 4, 5. Isolated electron energy level to the energy electron energy conduction band, valency band, and energy gap forbidden band. The upper band of the solid lines of the figure 1-5 can call the conduction band because of the electrons band, but they easily remove the application electrical fields. Materials have a large number of electrons conduction band as good conductors of electricity. Below the conduction band is the forbidden band energy gap. Electrons never found in this band, but must travel back and forth through it, provided that they do not come to rest in the band level. The last band is valency band, composed of the sheaf of the energy level containing valency electrons. Electron bands are more tightly bound with the individual atoms electron in the conduction band. However, the electrons of the valency band, which can still be moved with the conduction band with the application energy and the use of less thermal energy, the more bands below the valency band, but they're more important to understanding the semiconductor theory, and the world does not discuss. The concept of the energy band, particularly important with the classifying materials of conductors, semiconductors, insulators. The electron can exist with the two energy band, with the conduction band, with the valency band. Also necessary to move the electron with the valency band with the conduction band, so they use the electron current with the energy. Enough energy carries the electron through the forbidden band with the forbidden band. With the separation between the conduction valency bands determine the substance of the insulator, semiconductor, conductor. Figure 1-6 show the use of the energy diagrams. See the difference with the insulator and the semiconductor. So the insulator conduction band, forbidden band, valence band, semiconductor conduction band, forbidden band, valency band, conductor conduction band, valency band. The energy diagram of the insulator show the insulator with a very wide energy gap. The wider the gap, the greater the amount of the energy required with the electron with the valency band with the conduction band. Therefore, the insulator requires a large amount of energy to retain the small amount of the current. The insulator is because of the wide forbidden band with the energy gap. The semiconductor, on the other hand, small forbidden band requires less energy to move the electron with the valency band, the conduction band. Therefore, a certain amount of the applied voltage, more of the current will flow with the semiconductor than the insulator. And the last energy diagram is the 1/6 for the conductor. Notice that the forbidden band with the energy gap of the valence and conduction band overlap. No energy gap. It takes a small amount of energy to move the electron to the conduction band. Consequently, the conductors pass the electron very easily. Covalent band. Chemical activity of the atoms determine the number of the electron valency shell. The valency shell complete with the atom stability show with the little tendency for the combined with the other atoms of the solid. The only atoms positive the valencies have the complete outer shell. They are referred to as the inert inactive atoms. However, the valency shell of the atom lacks the required number of the electrons complete with the shell of the active of the atom and create the solid. In silicon and germanium, for example, the most frequent of these semiconductors, both quite similar with the structure of the chemical, the Hammer-Lewis, the 4 electron valency show the conservative just silicon. Since that fewer the required the number of the 8 electrons named in the outer shell of the atoms, you will unite with the other atoms until 8 electrons are shared. This gives the atom each of the total 8 electrons valency shell 4 of its own 4 that borrow with the surrounding atom. The sharing of the valency electrons between the 2 or more atoms are called covalent bonds between atoms. Is the bond with the holds the atoms together with the orderly structure called the crystal. Crystal is just another name for a solid which atoms molecules arranged in 3-dimensional geographical pattern, commonly referred to as lattice. Figure 1/7 show the typical crystal structure. Each figure is in figure representative of the nucleus atom with the arms joining the atoms supporting the structure and the covalent bonds. As a result of the sharing, the process of the valency electrons are held tightly together, best for illustrating the 2-dimensional view with the silicon lattice. Figure 1A, the circles from figure the representative of the nuclei atom, the plus 4, positive 4, a circle with the net chart of the nucleus, plus the inner shell with the minimum valence shell. The short lines indicate valency electrons. Because of every atom of the pattern is bound with over the 4 atoms, the electron is not free, but the move of the electron, move of the crystal result with the binding of the most pure silicon, germanium, poor conductor electricity. The recent are not insulated as semiconductors as well. The proper application heat, the electrical pressure electrons can cause the break free of the bonds, move of the conduction band. At once, if the band is wandering aimlessly through the crystal. Or your conduction process. As stated earlier, the energy can be added to the electron by applying heat. Enough energy with the absorb of the valency electron pop to break some of the covalent bonds. One for the bond with the electron move of the conduction band, where the capability supporting electron and current of the voltage applied with the crystal will contain these conduction band electrons. And the electrons move through the crystal toward the applied voltage of the movement of the electron in the semiconductor referred to as electron current flow. There's still another type of the current with the there's still another type of the current in a pure semiconductor. The current occurs with the covalent bond with the breaking of the broken and valency is left of the atom. The missing valency electrons and the valency vacancy is commonly referred to as the hole. Hole is considered a positive charge because of the atom with the deficiency with one electron called the proton. The outer number of the electrons result of the hole with the chain reaction. Become the nearby electron proton breaks out of the covalent bond with the fill of the hole. They leave another hole. The another electron breaks and bond with the previous hole, leaving still another hole. Each of the time in the electron process, the fill of the hole enters the covalent bond. Another through the electron has moved from one covalent to the other. The most important thing to remember is that the hole is also moving. Therefore, this process of the conduction resembles the movement of the holes rather than electrons. It is then termed the hole flow. The short of the hole current flow with the conduction by hole is very similar. Electron flow, except for the holes, may be moved toward the negative potential opposite direction of that of the electron. Since hole flow results at the beginning of the covalent bond with the valency bond with the level of the electrons associated with the type of the conduction contained with the only valency band energy must have the remaining valency band. However, the electrons associated with electron flow with the conduction band energy can therefore move through the crystal in good analogy of the hole flow with the movement of the hole through the tube filled with balls. Alright, analogy of the hole fill show the ball number 1 remove space left between number 1 ball, 2, 3, 4, 5, 6, 7, 8, space above the number 2 ball, 2, 3, 4, 5, 6, 7, 8, the space number 3 ball, and backwards moving it, ball moving the space number the number 8 ball. Or when ball number 1 is removed with the tube of the hole left, the hole is filled with the ball with the number 2, which leaves it still in another hole. The number 3 moved in the hole with the ball by number 2. This cover is still another hole to appear with the ball 3 with the bars, and then notice that all the moving to the right side of the tube. This action continues until the balls have moved one space to the left, in which the time the hole moved 8 spaces to the right and came to a rest at the right hand end of the tube. In theory, just describe the two current carriers that were created with the breaking of the covalent bond with the negative electron positive hole. The carriers referred to the electron-hole pair since the semiconductor we have been discussing contains no impurity. The number of the hole to the electron hole of the pure pair is always equal to the number of the conduction electrons. Although in any other way to describe the condition where the no impurities exist by saying semiconductors intrinsically, and the term intrinsic is also used to distinguish a pure semiconductor that we have been working with one container impurities. Doping process. The pure semiconductor mentioned earlier is basically neutral. It contains no free electrons in it in its conduction band. Even with the application of thermal energy, only a few covalent bonds are broken, yielding relatively a small current flow. The more efficient bond with increasing current flow with the semiconductors by adding very small amounts of selected additives that generally no matter than a few parts million. The additives are called the impurities process. The adding of the two crystals is referred to as doping. Purpose of semiconductor doping is to increase the number of the free charge that move the external applied voltage of the impurity, increase the number of the free electrons, dope semiconductor, negative the N-type of the impurities, add the number of the N-type impurity. However, the impurity reduces the number of the free electrons, causing more holes, creates positive P-type semiconductor. The impurity, the added known as the P-type impurity, semiconductors are doped in the manner either N or P-type impurity, negative or positive impurities is referred to as extrinsic semiconductors. Or your N-type semiconductor. The N-type impurities allow for the extra covalency with electrons easily when added with the semiconductor material. In so doing, increase the conductivity of the material, contributing the free electron. The type of the impurity has 5 valency electrons. It's called the pentavalent impurity. Arsenic, antimony, bismuth, phosphorus, or pentavalent impurities. Because the material is given to donate with one of the electrons to the dope material, they also call the donor impurities. When the pentavalent donor impurity, like this arsenic, is added to germanium in the fourth covalent bond with the germanium atoms, the figure 1110 illustrates the showing of the arsenic atom AS in the germanium GE lattice structure with the note of the arsenic atom symmetry lattice for the 5 valency with electrons outer shell with only 4 of them from the covalent bond with the germanium atoms, leaving 1 electron relatively free with the crystal shape. Crystal structure pure germanium may be converted to the N-type semiconductor doping with any of the donor impurity with having 5 electrons in the outer shell. Since the type of the semiconductor N-type has surplus of electrons are considered to have the majority of the character, the whole of the being the fewer number than the minority character. Figure 110 shows the germanium crystals doped with the arsenic, the excess of electrons. P2 type semiconductor. The second type of the impurity with the have the semiconductor material is ended to compensate for the deficiency of 1 valency electrons acquiring with electron with a neighbor. An impurity with the type of the only having 3 valency of electrons called the trivalent impurities. Aluminum, indium, gallium, boron, trivalent impurities. Because of the materials of 1 except 1 electron with the dope material, they also have called acceptor impurities. A trivalent acceptor impurity element can also be used in dope germanium. In this case, the impurity of the 1 electric short they require the electrons are needed with the equivalent established covalent bonds with the 4 neighboring atoms of the single covalent bond, and they will only be 1 electron step 2. The arrangement leaving in the hole for the covalent bond, figure 11.1, illustrates the theory showing what should happen to the germanium dope with the iodine atom with the notes for the iodine atom in figure 1. Electron shorts, and it requires the amount of electron needed to covalent bond with the 4 neighboring atoms. Therefore, create the hole in the structure of the gallium and the boron, and also trivalent impurities exhibit some of the same characteristics of the atom of the germanium. The hole that only can be present on the type of the semiconductor, the trivalent impurity. Note that the whole carrier is not created with a removable electron with a neutral atom, but is created with the trivalent impurity as the entrance of the covalent bond with the trivalent. Tetravalent, 4 valency electrons crystal structure. The holes of this type of the semiconductor positive type are considered majority carriers since they are present material in the greatest quantity. The electrons, on the other hand, are minority carriers. Or your semiconductor diode. If we join with the N-type of the semiconductor material with a simple section of the P-type semiconductor, we obtain the known as the PN junction, or they are known as the negative and positive region being the property to call the junction. The usual characteristic device that may be extremely useful electronic diode rectifier the diode for rectifier to the PN junction. Diode performs the same function with the counterpart of the electron tube with a different way. The diode is nothing more than 2 elements semiconductor devices that make for the rectifying property of the PN junction with a converting alternating current with a different current with a permitting current flow in only one direction. The schematic symbol for the PN junction diode shown with figure 112 with the vertical bar with the representative of the cathode N-type material. Negative type material, since it was the source of the electrons are here with the representative of the anode. Positive type of the material Since the designation of the electron of the CR1 alphanumeric code is identified with the code identified on the diode. The figure will only have the diode is labeled the crystal rectifier number 1. If you were to have 4 diodes shown in the diagram, the last diode would be labeled the crystal rectifier number 4. They'll have the dark line showing the electron flow. Notice that the against the arrow further classification pictorial diagram of the p-n junction and actual semiconductor, and one of many types that they are illustrated. Figure 112 shows your p-n junction diode. Shows the crystal rectifier number 1 electron flow with the cathode and the anode. See cathode and A anode schematic view. p-n junction N type and P type pictorial view, actual view. Alright, construction. Merely pressing together any section of the section of the positive material with the section of the negative material. However, it is not sufficient to produce the rectifying junction for the semiconductor. There should be one P from the proper positive negative junction, but divide the positive type of the impurity region from the negative type of the impurity region. This can be done in various ways. One way of this is mix the positive type of the negative type of impurities with a single crystal during the manufacturing process. By doing so, the positive region is grown. One part of the semiconductor lane with the negative region is grown over the other part. This is called the growing junction. Illustrating view A with the figure 113. Another way of the producing a p-n junction is to melt one type of the impurity into a semiconductor of the opposite type of the impurity. For example, the pellet with the acceptor impurity of the plate of the wafer, or negative type of the germanium, the heat of the unit controlled temperature for the condition of the acceptor impurity freezes with the wafer to form the positive region within it. Shown view B, figure 113, the typical type of the junction known as an alloy-fused alloy junction. One of the most commonly used junction, figure 114, point of contact type of the construction shown consists of the fine metal wire called the cat whisker, as makes the contact with the small area of the surface of the negative type semiconductor. Shown view A of the figure with the positive negative union is forced onto the positive process monetarily applied with a high surge current to the wire with the negative type of the negative type semiconductor. The heat generally contact current converts to the material nearest the point of the contact of the positive type material view B. Alright, 113 show the grown and fused positive negative junction for which the bars are cut. Now you have the grown ignite positive and negative cut into bars, and then the acceptor impurity pellet infused in specimens. Figure 114 show the point of the contact of the diode of the construction cat whisper negative and diode cat whisker positive negative, and so on. The process of the heat the section of semiconductor to near the melting with the diffuse of the impurity of the atoms of the surface layer, regardless of the process. The objective is held have the perfect bond with everywhere, and along with the union interface between positive and negative material with the proper contact allow. The union is important because we'll see later that the union, the junction, the interface with the rectifying agent and the diode. Positive negative junction operation. Now that you are familiar with the positive negative type of the material, these materials are joined together to form a diode with the junction of the diode. Let's continue the discussion operation of the positive negative junction. But we can further, before we understand positive negative junction, we must first consider current flow when the materials that make up the junction would happen initially with the junction with the two materials that are joined together. Current flow in the negative type of the material, the conduction of the negative type in semiconductor crystal or semiconductor conduction of copper wire. This is which is a voltage across the material. The electrons will move with the crystal as just as current would flow through copper wire. This is shown in figure 115. The positive potential of the battery will attract the free electrons of the crystal. Electrons will leave the crystal and flow in the positive terminal of the battery. Electrons leave the crystal with the electron with the negative terminal of the battery will aim the crystal with completing with the current path. Therefore, the majority current carrier of the negative terminal materials electrons are repelled with the negative side of the battery, moving to the crystal forward with the positive side of the battery. So 115 show the current flow of the negative type of the material from the negative to the positive goes to the flowing of the electron flow. Alright, current flow in the positive type of the material. The current flow with the positive type of the middle figure is illustrated in the 116 connection of the positive type of material with the positive hole with the inside of the negative electrons hole with the positive terminal with the positive with the negative terminal electron circle that either enter with the negative terminal with the material with the fill of the hole's vicinity of the terminal is positive terminal with the electrons removed with the covalent bond with the creating a new hole with the process continue with the state with the stream of the hole current toward the negative terminal. 116 show the current flow of the positive terminal, the positive going to the negative, and the electron flow through the battery. In order for them both, the negative and positive type of the material's current flow with the external circle, the current tip of the electron moving of the negative terminal battery with the positive terminal of the battery. hole in the flow with the other hand will only exist for the material itself. The junction barrier with another type of and although the negative type of the material will accept the free electron, circulate electrical neutron. This is because of the donor, and with the negative material that will left the positive charge of the free electron become available. The covalent bonding of the protons outnumber the electron. Therefore, the free electron with the negative material with the corresponding positively with the charge atom of the balancing the end of the result with the negative material with the overflow of the charge of the zero. But the same reason for the positive type of the material electronically neutrally because of the excess of the holes material with the excellently balanced with the number of electrons. Keep in mind with the holes of electrons are still free to move material because they are only loose bound to parent atoms. It would seem that if you join negative and positive material together with one of the processes mentioned earlier, the hole for the electron would pair up. On the contrary, this does not happen. Instead of the electron, the negative materials diffuse the more spread out across the junction into positive material, while they fill some of the holes. At the same time, the holes of the positive material diffuse across the junction. The negative material are filled with the negative material electrons. This process is called junction recombination. They reduce the number of the free electrons hold in the vicinity of the junction because there is a depletion. A lack of free electrons holds in the air that is known as the depletion range. The loss of the electron of the negative type of the material carried with the positive ion in the negative material, while the loss of the hole of the positive material created the negative ion in the material. The ions are fixed in place with the cross lattice structure cannot move. They make up the layer fixed charge of the two sides of the junction, shown in Figure 117. On the north side of the junction, neutral side of the junction, there's a layer with the positively charged. On the positive side of the junction, there's a layer negatively charged ions. An electrostatic field with the representative of the small battery in the figure established across the junction because of the opposed charge ion of the diffusion electron hole with the across the junction will continue with the magnetic magnitude of the electrostatic field increase at the point with the electron hole with no larger than enough of the energy to overcome the repel the negative and positive ion respectively. At this point, with the equilibrium established, all practical purposes, movement that carries across the junction cave ceases for the reason electrostatic field with the created with the positive negative ions of the depletion region is called the barrier. Alright, 117 show the positive negative junction barrier information junction positive negative depletion region electrostatic field 0 is the plane holds and O negative is a free electron hole space with a one horizontal line is a negative ion hole space with a positive sign is a positive ion. Alright, the action described will occur with the almost instantaneous with the junction form, and only the carrier immediately with the same with the junction effect with the carrier, though throughout the remainder of the negative impact of the material relatively undisturbed and remain balanced condition. Forward bias, an external voltage of the applied with the positive and negative junction with called the bias. For example, the battery is used with the supply with the positive negative junction connection with the voltage applied above the junction field, they will reduce the junction barrier. Therefore, the current aid current flow for the junction from the type of the bias known as the forward bias of the top of the junction that offer only minimum resistance flow of the current. Alright, your forward bias is illustrated in Figure 118. Notice with the positive the terminal of the bias of the battery is connected with the positive type of the material, negative battery terminal in the battery connected with the negative type of the material. The positive potential of the repel toward the junction of the neutral sum of the negative ions. At the same time, with the negative potential will repel the electron toward the junction with the neutralized sum of the positive ions. Since the ions on both sides of each of the carrier are being neutralized, the width of the barrier, the decrease of the loss of the effective of the battery voltage, the forward bias direction is reduced the barrier potential with the cross of the junction. Allow the majority of the carrier to cross the junction current flow into the forward bias of the positive negative junction in the relatively simple electron leave with the negative terminal of the battery, move the terminal of the negative type of the material, and for the negative material with the majority of the carrier to move the edge of the junction barrier. The cap of the forward bias of the barrier offers the left of the opposition of the electron and will pass the depletion region of the positive type of the material. The electron leave with the energy overcoming the opposition of the junction barrier upon entering the positive material combined with the hole is produced with the electron will extract the positive material the positive the potential of the battery. Created holes move through the positive material toward the junction where it combines with the electron. Alright, 118 show the forward bias, positive negative junction flows in between the positive and negative side terminal depletion range, original barrier, electron flow. It's important to remember the forward bias of the condition is the majority of the current carrier of the whole of the positive type of the material, electron negative type of the material, increase of the battery voltage with increase of the time of the majority of the carrier areas across the junction throughout there, increase of the current flow of the battery voltage, increase the point of the barrier is greatly reduced, and a heavy current will flow with the junction can be damaged with the resulting may be damaged from resulting heat. Your reverse bias. A battery maintained with the earlier and connected across the junction so that the voltage A of the junction, they will increase the junction barrier, thereby offer the high resistance of the current flow through the junction. The type of the bias is known as reverse bias. To reverse a bias junction diode with a negative battery terminal connected with the positive type of the material with the positive type battery terminal, the negative type of the material with the shown figure 119, the negative potential of the track of the hole of the way from the edge of the junction barrier with the positive side of the positive potential of the craft of the light surrounds away from the edge of the barrier with the negative side of the action increase of the barrier with the will with the brace because of the more of a negative volume with the positive side of the junction, the most positive volume with the negative side of the junction. They will notice the figure width of the barrier increase of the number of the prevents the current flow of the junction majority carry the however the current flow of the across the barriers is not quite zero because of the majority of the carries across the junction. As you recall with the critical crystals is subject to the external source of the energy of the light and heat with the electron hole pairs are generated electron hole pairs are produced with the minority current carrier with the minority current carriers in the both region of the neutral in the negative material electron positive material of the reverse bias electrons the positive type of the material repelled the junction with the negative terminal of the barrier as the electron moves across the junction the neutralize the positive ions with the negative type of material similar that hole of the negative type of the material will be repelled with the positive type of the positive terminal of the barrier toward the junction as the holes create across the junction neutralize with the negative ion the positive type of the material of the movement of the minority called the minority current flow because of the hole of the electrons involved with the coming from the electron holes are a pair of the generated with the crystal lattice structure not from the addition of the impurity of atoms. Alright, 119 show the reverse bias of the positive negative junction depletion range and original barrier. Therefore, your positive negative junction reverse barrier, there will be no current flowing with the majority of the carriers with a very small amount of the current. The majority carriers cover the junction. However, the normal operating temperature of the small current may be neglected. In summary, the most important point to remember the positive negative junction diode's ability to offer the very little resistance current flow with the forward bias direction, maximum resistant current flow with reverse bias with a good way to illustrating the point of the plotting the graph of the applied voltage reverse measure of the current. Figure 120 shows the voltage current relationship with the character curve of the typical positive and negative junction diode. Positive junction diode characteristic curve of the reverse current on the bottom, forward current above in your positive regions. You have a line starting at 80 volts, moving for 40 volts, and then to a forward bias on the forward side of the current. You have points A and B to determine the resistance of the curve of the figure with the Ohm's law. For example, which would be ohms equals amps ohms equal to volts over the amps. For example, the point with the forward bias over the voltage 1 volt with the forward bias current with the 5 milliamps that represents 200 ohms of resistance, 1 volt with the 5 milliamps of 200 ohms. However, the point of the B, the volt with 3 volts, current 50 milliamps. The result of the 60 ohm resistance with the diode with the notice of the forward bias voltage will be triple 1 or 2, 3 volts. The current increase of 10 times the 5 milliamps to 50 milliamps. At the same time, the forward bias voltage increases the resistance decrease of the 200 ohms to 60 volt ohms. The four other words, the forward bias increases the junction barrier, the greater smaller into the in other words, the forward bias increases the junction barrier gets smaller and the resistance of the current flow decreases. On the other hand, the diode conducts very little with reverse bias, very little when reverse bias. Note that the C reverses the reverse bias voltage is 80 volts with the current only with 100 microamps. The result of the 800 kiloohms of the resistance considerably larger resistance for the junction with the forward bias. Together with the unusual feature of the positive negative junction diode is often used in converting alternating current into the direct current rectification. Alright, your positive and negative junction application. Until now, they mentioned only the application of the diode rectification. There are many with more of application that you have to discover the variation of the doping agents and semiconductor material manufacturing technique has been possible to produce the diode that can be used with different applications. For example, the type of the diodes, the single diodes, rectifying diodes, zero diodes, voltage protection diodes for the power supply reactors, applying with the switching diodes. There are many more only applications for the two more commonly used diodes. The single diode and rectifier valve will have the present in the chapter. The other diodes will be explained later in this module. Halfway rectifier, and the most important, the use of the diode rectification, the normal positive negative junction diode, well suited with the force with very little heavily with the forward bias, low resistant direction, only slightly with the reverse of the bias, heavy resistant direction. In play for the diode, here with the source of the AC power with the diode will forward the reverse bias every cycle. Since the situation current flows easily with one direction, the other the rectification is accomplished. Simple as rectifier current is a halfway rectifier, figure 122, view A and view B, with a consist of the diode over the AC power source of the load resistor. Figure 121A, simple half wave rectifier. You have your fuse, AC input, transformer, iron core, your crystal rectifier, your resistant load output wave, AC input, fuse, transformer, series crystal rectifier, resistant load. Symbol half wave rectifier, positive and negative. Alright, the transformer, the T1, provided by the AC input, by the circuit with the diode, with the crystal, the diodes, CR1, produced for the rectification load resistors, over the two purposes, the limited amount of the current fluid, with the circuit with the safety level, will also develop the output signal, because of the current flow through it. Before describing how the current circuit operates, the defining the word load applied with the power with the supply must be understood. The load is defined as any device that draws the current. The device that draws little of the current is considered a light load, with where the device that draws a large amount of the current is a heavy load. Remember that we can speak with a load, but we are speaking about the device that draw current through the power support of the devices. Of the simple resistor one may be complicated with electronic circuit with the device. During the positive half cycle, the input side signal of the solid line with the figure 121 view A with the top of the transformer, the power with the respect of the ground, the diodes transform, the indicating point with the same, the polarity, the condition of the diode is forward, base depletion region, the narrow, the resistance of the diode load is low with the current flow of the current circuit, the direction of the solid line with the current of the flow of the load resistive valve, the negative and positive voltage drop across which appear with the positive voltage of the output terminal. The AC input with the negative direction of the figure 121 view A with the top of the transformer become with the negative diode, become with the reverse bias, the reverse bias applied with the diode application, reverse diode, reverse biode, the depletion of the region, the depletion region increase the resistance diode is high with the minimum current flow for the diode for all particular purpose. The nose input with the develop of the load resistor during the negative alteration. The input signal is indicated with the broken line with the figure, although one cycle with those inputs shown with the relay of the action with the described above the circular continually the respectively repeats itself along with the input. Therefore, the signal since only a half positive for the half cycle will appear with the output of the circular and is converted with the AC input into the positive oscillating DC voltage frequently output voltage equal to the frequency of the applied AC signal. Since there is one pole to each of the signal, each cycle with the AC input with the example the input frequency is 60 Hz per cycle, output frequency 60 pulse per second. However, the diode is reversed and shown with the UB with the figure 121 with the negative output voltage that would be the obtained with the current would be flowing from the top of the resistor load resistance top of the bottom of the making output of the load top of the load resistance negative with respect to the bottom of the ground. Because of the current flows in the circuit only half of the during half of the input cycle is called the halfway rectifier. Alright, the semiconductor shown in the figure with the relay with the metallic rectifier with still achieving the same as the result of the metallic rectifier, sometimes referred to as the dry disc rectifier, metal to metal. Metal is a semiconductor large area with the contact of the device with the construction distinctive of the semiconductor, sandwich between the two metal plate with the electrode is shown figure 122. The note with the figure with the barrier with the resistance many times with the greater with the semiconductor material instructed one metal electrode with the contact heavy with the barrier with the rectifying with the contact other contact with the non-rectifying metallic rectifiers act with the diode previously discovered the permanent current with the flow for the more readily one direction than the other. However, the metal rectifier very largely compared to the crystal diode can be shown in figure 123. The reason for this is metallic rectifier units are stacked and prevent inverse voltage breakdown. However, the larger area that handle with the high currents usually have cooling fans to prevent overheating. Show the 122 show the metal rectifier, a barrier, semiconductor, non-rectifier, metal and electrode rectifier, metal electrode. Alright, metal rectifiers, and the crystal rectifier for the ceramic and cartridge type and pigtail types. There are many no metal semiconductor components that give you the contact of the rectification. Copper oxide, selenium devices are far from the most popular. The carbon oxide with the selenium are frequently used, though other type of the metallic rectifiers because they are large forward with the current per unit with the contact with the air with the large forward voltage drop with a good stability with the lower aging rate. With the practical application for the selenium rectifiers with a relatively large amount of the power is required. On the other hand, the copper rectifiers are generally used small current applications such as the AC meter movements for the delivering during the direct current of the circuits requiring more than 10 amperes. Since metallic rectifiers are affected with the temperature of the atmosphere condition for the aging, within this case, the copper oxide selenium being replaced with improved with the silicon crystal rectifier. With the silicon rectifier is placed with the bulky selenium rectifier with as to the current voltage rating, and it can be operated with a higher ambient current surrounding temperatures. Alright, a diode switch. In addition to the simpler rectifier, the diodes with the rectifier with the mix of the signal together with the mixer with the presence of the signal detectors. They actually switch to the open and close circuit of the diodes for the use of the application for the commonly referred to as signal diodes. Simplest application of the signal diode is the basic diode which shown in figure 124. 124 shows the output output voltage, input voltage, and your current flow from the crystal rectifier 1, load resistance positive, over voltage with the crystal 1 conducting output with the voltage, positive voltage, crystal 1 cut off the open switch, closed switch, basic diode switch. When the input of the circle is 0, potential for the diode, the force of the bias to be covered with 0 for the potential for the cathode, pi for the voltage for the anode, is indicative for the diode, for the conductor, the axis, out of the straight piece of the wire to be covered with a very low forward resistance. In effect, the input is directly coupled with the output, resulting in 0 to cover the output terminal. Therefore, the diode acts as close to such which the anode positive with respect to the cathode. If we apply the positive input equal with the greater or less greater than the positive voltage, it will be applied with the anode of the diode. The cathode of the diode will be reversed by with the in situation diode call the axis of the open switch between the input and the output terminals. Consequently, no current flow with the circuit applied with the voltage of the diode anodes will be felt with the output terminal. Therefore, the diode acts upon an open switch with a reverse bias. Alright, diode characteristics. Semiconductor diodes have properties that enable them to perform many different electronic functions they do. Their job, the engineer technicians must be supplied with the data with a different type of the diode, with the information presented with the strip of the diode characteristics supplied with the manufacturer, any of the manual with the specification sheet of the data sheet. Because of the score of the manufacturer's number and type of the diodes, it must be particular to put before your specification sheet and call it typically as a side of the difference between the manufacturer single the manufacturer's not evenly specification sheet the differ the most format and content. Despite the difference in certain performance, the design information normally required will discuss the information in the next few paragraphs. A standard specification sheet with the usually produced description of the diode include the description of the type of the diode, the major of the major area of the application, any special features, or the particular interest of the specific application in which the diode is suited. The manufacturer also provides the drawing of the diode with the given dimensions, weight, and if appropriate, identification marks. In addition, above the diode, the following information is provided with a static operating table to give the spots value of the parameters under the fixed conditions. Sometimes the characteristic curve is similar to the one figure in 120, showing how the parameters vary over the full operating range of the diode ratings, which are limiting the value for the operating conditions outside of which cause the diode damage. Manufacturers specify the various diode operating parameters character for the letter similar in accordance with the fixed definition of the following lift of the letter similar to other major electrical character for the rectifier signal diodes. Rectifier diodes. DC blocking voltage or VR, maximum reverse DC voltage will not cover the breakdown. Average forward voltage or VF. AV. The average forward voltage drop of the cutoff of the rectifier given the specified current temperature. Average rectifier forward current. They would have to show the amp symbol with an F for forward AV for average. Average rectifier forward current or the specified temperature as usually a 60 Hz will resistive load. Average reverse current. Show the amps with an R and an AV for the average reverse current amp. The average reverse current is specified with the temperature usually 60 Hz. Peak source surge, amp surge. The peak current is specified and given the number of the cycles employing the peak. Your single diodes, peak reverse voltage, or PRV, the maximum reverse voltage that can be applied before reaching the breakdown point. That is the peak reverse voltage. Also applied with the rectifier diode. Rectifier reverse current, or amp R, small value with a direct current flow of the semiconductor diode, the reverse bias. Maximum forward voltage drop indicated the forward current or voltage forward at amperage forward. Maximum forward voltage drop at the cutoff of the diode indicated the forward current. Alright, reverse recovery time or TRR, maximum time for the forward bias diode to recover its reverse bias. Reading the diode stated earlier with the limiting value of the operating condition where they exceed the coding damage of the diode with either voltage breakdown or overheating positive negative junction. Diodes generally rated with the maximum average forward current, peak recurring forward current, maximum surge current, and peak reverse voltage. Maximum average forward current is usually given in a special temperature, usually 77 degrees Fahrenheit, referred to the maximum amount of the average that can be permitted to flow with its forward with the direction rating and exceed with the structural breakdown can occur. Peak recurrent forward current, the maximum current that is permitted to flow in the forward direction of the form and the recurrent pulses. Maximum surge current, the maximum current permitted to flow with the direction of the forming of the non-recurring pulse of the current should not equal the value of the field. more than a few milliseconds. Peak reverse voltage is one of the most important ratings. The peak reverse voltage indicates the maximum reverse bias voltage that applied to a diode will causing junction breakdown. All of the above ratings are subject to change with the temperature variations. In the example, the operating temperature is above the stating ratings. The ratings will be decreased. Diode identification. There are many types of the diodes verifying the size of the pinhead, the subminiature with the Alright, there are many types of diode with various angles of the bin end, the some miniature with the circuit with the large, the 250 amp diode with the high power circuit with the there are many different types of the diode, say some of the identification they need with the distinguish one diode from the other. There's accomplished with a semiconductor identification system. Shown in figure 125, the system is not only with the diode with the transistor many other semiconductor devices. As illustrated in the figure, the system with the number of the letters identifying the different type of the semiconductor. The first number of the system indicates the number of junctions within the semiconductor device, the number of number one. The semiconductor device is a number. One less than the number of the active elements. Thus, the 1 designates the diode, 2 designates the transistor, which may be considered made of the 2 diodes, 3 as a designated the tetrode, or the 4-element transistor, 5 the following first number they indicate the semiconductor. The 2 or 3 digit following the letter N is serialized identification number that is needed, and if needed, the number may contain suffix letter at the last of the digit. For example, the suffix N may be used with the dispatching matching parts to separate the semiconductor devices. Lettering R may be used to indicate reverse polarity. Other letters are used to indicate the modern version of the devices, which can be substituted with the maximum base number unit. For the example, the semiconductor diode designated type 1N355A is simply is a simple 2-element diode of 1 of the semiconductor material, and if that is improvised with a version A of the type 345. So X is your component with the semiconductor junctions, and the N is the semiconductor, and the N is the semiconductor. YY is the identification number, the ordered registration number. Also can is stuff with the applicable identification. 1 matching device, 2 reverse polarity, 3 modification. Alright, when working with a different type of the diodes, it's necessary to distinguish one end of the diode with the other anode or from the cathode. For the recent manufacturer general code of the cathode end is K or positive cathode, the color dotted band with the unusual shape of the raised edge or taper as shown in figure 126. So, in case of the standard color band with the plate for the cathode and the diode serve with the 2 purpose identifying with the cathode and with the diode, also serve with identifying the code. Diode over the number. Show over the band, the mark, color, spot, color, bands, glass, mark, anodes, cathodes. 2 standard diode color coded shown in figure 127. The typical take of the example of the diode was a brown, orange, and white band over the terminal figure of the identification number. White, brown being 1, orange 3, white 9. The device would identify the 139 semiconductor diode, specifically 1. A diode and negative terminal, 1 for your orange, 3 for your 1 for orange, brown, orange, and white. Alright, they have a digit. 0 is black, brown is white, 0 is black, brown is 1, red is 2, and then 3, 4, orange, yellow, 3, 4, yellow, 5, green, 5, 6, blue, 7, violet, 8, gray, 9, white, and then from 1 to 9 is A through J. Keep in mind whether the diode is small crystal type with large power rectifiers, both are still represented schematically. You explained earlier with the schematic shown figure shown in 112. Or your diode maintenance. Diodes are regularly deficient, but they are also expected to be relatively trouble-free. But the periodic encapsulation process of the special coating of the technique have either further increase the life of the expectancy in theory with the diode. There should be intent. And lastly, identified how the diodes are subject to the current they overload with the junction damage the destroyed. In addition, the application with excessively high with the operating voltage can damage the destroy the junction of the arc over the or excessive the reverse currents. With the greatest damage and danger of the diode heat, the heat cover the more external electron heat or hole to be generated, which in turn increase the current flow with the current increase the current generated more heat with the cycle repeats itself until the diode draws excessive current. The action is referred to as thermal runaway. Eventually, the current called the diode destruction. Extremely caution should be used with working equipment containing diodes to ensure that problems do not occur with the cause of irreparable damage. Diode damage. Following list are some of the specific safety precautions that should be observed when working with the diodes. Never remove the insert of the diode onto a circuit without the voltage applied. Never pry diodes to dilution from their circuits. Always be careful to solder when soldering to ensure that excessive heat is not applied to the diode. When testing the diode, ensure the testing voltage is not exceed the diode's maximum allowable voltage. Never put fingers across with a single diode because of the static charge of the body could short the diode. Always replace the diode with a direct replacement with one of the same type. Ensure the replacement diodes are put into the circuit into a correct direction. If the diode has been shuffled at excessive voltage, the temperature suspected of being defective, they can be changed, checked in various ways. The most convenient, corrective, quickest way of the testing of diodes is with the ohmmeter to make check for the sum and stains. Simply disconnect one of the diode lead with the circuit warning with making the resistant measure across the lead of the diode. The resistant measure will obtain with the depending on the lead test lead of the polarity of the meter. There are two measurements that must be taken. The first measurement is taken from the test leads containing either the test either end of the diode. The second measurement is taken from the test lead reverse of the diode. The largest resistance values assume the reverse back resistance of the diode. The smaller resistant front value is assumed to be forward resistance. Measure can be made with the corresponding comparison purpose of another identical type of diode known to be good. A standard too high value resistant measurement indicates the diode is open and high forward resistance. Too low voltage, but too low value resistant measurement indicates the diode is shorted and low reverse or has low reverse resistance. Normal set of measurements will show high resistance in reverse direction, low resistance in forward direction. The diode efficiency is determined by how low the forward resistance compared with the reverse resistance. This is desirable to have the ratio, often known as front-back ratio or back-to-front ratio, possible between the reverse forward resistance measurement. However, the rule of thumb is a small single diode will have a ratio of several hundred to 1, while a power rectifier can operate satisfactorily with a ratio of 10 to 1. Show the reverse condition of the highest resistant diodes and test leads from the ohmmeter, and then the forward condition would be on the other side of the ohmmeter from your forward condition low resistant measurements. Alright, one thing you should keep in mind with the ohmmeter check is not conclusively. It is possible to check with for a diode to check good and it would break down when the place the end bake and the check with the problem is that the meter you the check of the diode with low voltage for the diode usually operates in the circuit. Another important point to remember is that the diode should not be condemned by two ohmmeters. Should not be condemned because the two ohmmeters give the different readings of the diode. They occur because of the different internal resistance of the ohmmeter, the different stage of the charge of the ohmmeter batteries, of the ohmmeter, the sum of the different current of the different through the electrode. The two resistant values read with the meters will not be the same. Another way of checking a diode is with the substitution method. The method is a good diode substitute with a questionable diode, but the technique should be used only for this, but only after you have made voltage and resistant measurements to make certain that there is no circuit defect that might damage the substitution diode. If more than one defective diode is present with the equipment section where the trouble that has been localized and the during becomes cumbersome, the trouble the diodes may either have it replaced before the trouble is corrected. Determine that it stayed and failed with the diode that is not defective at all, but they can remove the diodes that must be tested and accomplished by observing the equipment and operate it correctly as remove the diodes and reinsert it into the equipment. In conclusion, only the valid check of the diode dynamic electrical testing determines the diode forward current resistance, reverse current resistance parameters. This test can be accomplished using various crystal diode tests that are readily available from the many manufacturers. And Chapter 1 summary.